Hello friends, in today's question, a simple pendulum is made of string length L and a bob of mass M is released from a small angle theta naught. It strikes a block of mass capital M kept on a horizontal surface at its lowest point of the oscillation, elastically. It bounces back and goes up to an angle of theta 1, then M is given. So we have these four options. So, in the first case, when the pendulum is released from the angle of theta naught. Okay. So, this is the vertical position and we have a pendulum. The angle is given as theta naught. This is the mean position, here where the mass M is kept, and L is the length of the string. So we can find out the height through which the pendulum is going to fall from its mean position or towards its mean position. Let us suppose this is given as h. Therefore this height will be given as L minus h. So let us consider the first case. First case, the pendulum is released from the angle of theta naught. Pendulum is released from an angle of theta naught, and we assume that the speed of this pendulum at its lowest point, let us suppose, is given as v. The pendulum is released from an angle of theta naught. Therefore we can say its height from the mean position let us call this as point as O, this as A, this point as B, and this point as C. So its height from the mean position will be equal to BC, which is equal to H. Okay, because this height is also H. And we also assume that velocity at the lowest point, velocity at the lowest point B is given as V. So therefore we can use conservation of energy. Conservation of energy. We have potential energy at point A will be equal to kinetic energy at point B. Okay, because at point B the potential energy will be equal to 0 and at point A its kinetic energy will be equal to 0. So we can say potential energy at A will be equal to kinetic energy at B. So potential energy at A is given as mgh and kinetic energy at B will be given as half mv square. Here mass cancel out with mass, therefore we can say that V square is equal to 2GH. Now if you consider triangle AOC, we can find out the cos of theta naught. In triangle AOC, cos of theta naught will be equal to L minus H divided by L, and cross multiply it, we get L cos of theta naught is equal to L minus H. From here we can say our H is equal to L 1 minus cos of theta naught. So we substitute the value of H in this equation. So therefore we get V square is equal to 2GL 1 minus cos of theta naught, or simply we can say our velocity V is equal to 2GL 1 minus cos of theta naught and its square root. Let us call this equation number 1. Now it's given that at its lowest point the pendulum strikes a mass m. Says at lowest point pendulum strike mass capital M. So it means this is pendulum of mass m traveling with velocity v, and we have mass m whose velocity is equal to 0. And after collision it is given that this pendulum mass m travels in the opposite direction, let us suppose with velocity v1, and mass capital M travels forward with the velocity v2. So this is our before collision and this is our after collision. So herein we can say that we can use conservation of momentum, or we can simply again find out the equation of the relationship between the velocity v1 as well as for the length and the angle theta 1. Okay. So this is our pendulum and this is our mass. Pendulum and mass. Now once again we can say, or rather it is given, that after collision the pendulum travels through the angle of theta 1. So we can consider a second case, which after collision pendulum makes angle theta 1. So we can once again draw the figure. So this is our vertical and we have a pendulum and this angle is now theta 1. This is a mean position. Now the pendulum is traveling in this direction and we say now the height, let us suppose, is h1, and once again this will be L minus h1, okay, and its velocity with which it is moving in this direction is v1. Using similar equations we can find out cos of theta 1 and try to solve it. We are going to again get the same relationship but with the angle theta 1. So you can say similarly v1 will be equal to 2gl 1 minus cos of theta 1 and its square root. Let us call this as equation number 2. So here we can, if you see equation 1 as well as equation number 2, the height factor does not matter. Okay, it is only dependent upon the g as well length and cos of theta 1. Okay, the height to which previously it was h, but still the relationship was only dependent upon gl and cos of theta 1, and here now height is supposed different h1, and once again it is only dependent upon l and theta 1. Now it is given that the collision between these two is elastic. You can say collision between pendulum of mass small m and mass capital M is elastic. So it is elastic, which means coefficient of restitution, that is E, will be equal to 1. And we already know the formula for E. E is equal to relative velocity after collision divided by relative velocity before collision. So you can say relative velocity after collision divided by relative velocity before collision. So after collision we have velocity v1 and v2 and they are in opposite direction, whereas before collision there is only the relative velocity is for pendulum is v, whereas for mass it is 0. So we can write that 1 will be equal to v2 minus minus of v1 divided by v minus 0, or we can say v is equal to v1 plus v2. Let us call this as equation number 3. So we already know the value of v1 as well as v. We can find out value of v2. So using equation 1 and 2, using equation 1 and 2 in equation 3. So v is when the angle was theta 1, theta naught. So we can write this as 2gl 1 minus cos of theta naught square is equal to v2 plus v1 was theta 1, 2gl 1 minus cos of theta 1 and its square root. So we can write from here that v2 is equal to 2gl is common to both the equations, both parts left and right, so it will be 1 minus cos of theta naught minus square root of 1 minus cos of theta 1. Let us call this equation number 4. Now we can use further conservation of momentum and find out further relation. You can say using conservation of momentum. So we already know that pendulum having mass m was traveling with the velocity v, and capital M was having its velocity as 0, and after collision mass m is traveling with the velocity v1 and mass capital M is traveling with the velocity v2. So this we have before collision, and this we have after collision. So we can say mv plus 0 is equal to mv2 minus mv1. So here we can say mv2 will be equal to mv plus v1. Now we already know the value of v and v1 in equation 1 and 2. You can say using equation 1 and 2 we get mv2 is equal to m. V is or with respect to theta naught, so we can write it as 1 minus cos of theta naught plus 1 minus cos of theta 1 and the common term 2gl. Let us call this equation number 5. So we divide equation 4 by 5. Dividing equation 4 by 5, we get this will be equal to v2 divided by m times v2 and square root of 2gl, and inside the bracket we have 1 minus cos of theta naught minus 1 minus cos of theta 1, and here we have m 1 minus cos of theta naught plus 1 minus cos of theta 1 and square root of 2gl. 2gl cancels, v2 cancels, so we can say from here m divided by capital M is equal to 1 minus cos of theta naught square root minus 1 minus cos of theta 1, and we have 1 minus cos of theta naught plus 1 minus cos of theta 1. We can use trigonometric identity and we get this as m upon capital M. This will be sine square theta naught by 2, minus, so this will be sine square theta naught by 2. So we get sine square theta naught by 2 square root minus sine square theta 1 by 2 square root, and here also we get sine square theta naught by 2 square root plus sine square theta naught by 2 and its square root. So square root will be cancelling out and we will be left with m upon capital M will be equal to sine of theta naught by 2 minus sine of theta 1 by 2 divided by sine of theta naught by 2 plus sine of theta 1 by 2. Now in the question, it is given that the angle is very small. Okay. So you can say for small value of theta naught and theta 1, the sine theta naught by 2 can be approximately equal to theta naught, and sine of and theta 1 by 2 can be approximately theta 1 by 2. Therefore, we get m upon capital M will be equal to theta naught by 2 minus theta 1 by 2, and here also theta naught by 2 plus theta 1 by 2, which is equal to theta naught minus theta 1 divided by theta naught plus theta 1. And we are supposed to find out the capital M. So we can say from here our capital M is equal to m times theta naught plus theta 1 divided by theta naught minus theta 1. This is our final answer, and it was supposed to find out the mass M. So this is the mass M, and from option you can say that option number A is the correct option. Option A is correct. This completes the question. Thank you.